Hello everyone and welcome to FPGA real-time control and digital signal processing tutorials. In this tutorial I will explain you how to implement pulse width modulation by using FPGA and Verilog programming language. For example, over here you can see pulses with a period of 500 milliseconds and with a width of 200 milliseconds. Over here, you can see a simple circuit I created that's used to visualize pulse width modulation. This circuit consists of LED and 330 ohm resistor. There are only two wires coming out of the FPGA. Observe this PMOD port. This black wire is the ground wire, and the blue wire is the signal wire, and the pulse width modulation signals are transmitted through this wire. I will provide a more detailed explanation of this basic circuit and all the connections later on in the video. Before I start, I would like to mention a few things. Those of you who are my subscribers or who follow my work know by now that I always create a post that nicely summarizes everything that I will explain in this video. And consequently, here is the post. This post contains figures, Verilog code, and all explanations. A link to this post is given in the description below. Secondly, it took me a significant amount of time, energy, and planning to create this post and this video. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. First, I will explain basic circuit and hardware connections. This tutorial is based on Nexys A7 100T FPGA. You can find more about this FPGA by clicking on this link and by reading this page. Basically, it's a relatively low-cost FPGA that costs around $350. However, everything explained in this tutorial can easily be generalized to other types of FPGAs. The board is shown over here again. The connection of the board with the external breadboard is shown over here. So let us explain this circuit. This PMOD port over here is used to interface the FPGA with my breadboard. The ports of the PMOD are shown over here. This port over here is ground, and this is the signal. Basically, this is my signal, and this is ground. This wire over here will transmit pulse width modulation signals that look like this. It is important to keep in mind that the name of this pin is H4. This is very important for writing the constraint file, and this will be explained later on. Then, to visualize pulse width modulation signals, I created a small circuit over here. Basically, this circuit consists of 330 ohm resistor and LED. Basically, what happens over here is that once pulse width modulation signals are transmitted, and if this basically period is not very fast, when I say not very fast, I mean that this period is, for example, 0.5 seconds, then the LED will blink. Basically, the LED will blink when we have high voltage, and it will stop blinking when we have low voltage. Consequently, we'll have light, no light, light, no light, light, no light. Okay, so let's start with coding. Notice over here that I'm using Vivado 2022.1. Of course, you can use a newer or older versions. The principle is very similar. So let's create a project. Here I will click on Next. I will use the default settings. Here it's very important to keep this option on. Do not specify sources at this time. Click on Next. Let's find the boards. So you click over here and you search for your board. In my case, it's Nexys A7, and here it is. I will click on Next, and I will click on Finish. Okay, now we are ready to code. We need to create two files. The first file is our source file or the main file, and the second file is the constraint file. The source file will basically define the programming logic of our system, and the constraint file will be used to constrain the variables defined, or better to say declared, in the source file to the actual pins on our board. So let's create the source files. I will click on Add Sources, and over here I will select this option, Add or Create Design Sources, and I click on Next. Here I will click on Create File. I will call my file, let's say main file. You can choose other name if you wish, and I will click on Finish. And I will click on OK. Yes. And after some time, this window over here will update. We will click over here and we will double click over here. Then this window will pop up and here's our source file. So let us completely erase everything that's written over here. And in order to make this video as short as possible, I will basically copy and paste the code from the previous file I created. So here's my source file. I will copy and paste this file over here, and I will explain this file in details. This file is also given on my web page, that is, it's given over here. Here's the source file. Let us explain the source file. Here, I'm using the timescale 1 nanoseconds with the precision of 1 picoseconds. This is not important to understand for the time being. Then, here I define my module. Here's the beginning of the module, and here's the end of the module. The module has one input. The input is this variable CLK, which is a shorthand for clock, and the output is LED. This module will accept clock and it will produce a signal LED. Let us explain this module in more details. Basically, my module can be represented as a block. It accepts clock, CLK, and it produces the signal LED. The clock variable or the clock input will be constrained to the system clock. My current board has a clock of 100 megahertz. This means that the period of the clock is 10 nanoseconds. Let us visualize this graphically. Let this be a time axis t, and let this be clock. My clock signal looks like this. It's basically a very high frequency train of pulses, where this period over here is 10 nanoseconds. This clock is actually used as a reference to produce the pulse width modulation signals that this output LED is carrying. And the pulse width modulation signal will look like this. It will again be a train of pulses with this period denoted by T, and the pulse width, let's say denoted by T1, that are specified by the user. That is, T1 and T are specified by the user, and T1 and T are computed by using clock as the reference. So the clock is the smallest time unit that can be used to produce T1 and T. T1 over T is usually called a duty cycle. And let's say a duty cycle of 100% means that T1 is equal to T, that is, we have a constant DC signal. However, if, for example, T1 over T is 10%, this means that this signal is actually the pulse width is 1/10 of the period. That is, our pulse width modulation signal looks like this. After defining inputs and outputs, we need to define a counter. I will explain the counter in the sequel. Then, we need to define two integers, period length and pulse length. Basically, the period length is our T variable and pulse length is T1. Graphically, again, T1 and T are given over here. So this is T, and this is T1. This block over here is the always block that's used to increment the counter or to reset the counter. So let us explain this block. First of all, let us sketch our clock. Remember that a clock is nothing less than a train of pulses with a width of, or better to say with a period of 10 nanoseconds. Whenever a positive edge of the clock is detected, that is, whenever the clock goes from the low value to the high value, that is, this is the positive edge, then this part over here will be executed. And notice over here that we have non-blocking statements. This means that these statements will always run in the background. They will not run sequentially, they will run basically in parallel all the time. So let's see what happens over here. If the counter is smaller than the period length, then increment the counter. This means the following. Since we defined the desired pulse width modulation signal to look like this, where this is basically T and this is T1, this counter will basically increase until we come here. That is, until we reach the period length of 4000, and then the counter will simply reset. Okay, now we have a counter. Next, we need to produce a pulse width modulation signal. So let's see how to do that. Keep in mind that counter goes from 0 to period length, then it resets in the next period, and again it counts from 0 to the period length. So how to produce a pulse width modulation signal? Basically, we can produce the pulse width modulation signal by using this code line. So this code line is basically an if statement. If counter is smaller than pulse length, and the pulse length is given over here, and let us graphically again visualize the situation. So this is our T, that is period length, and this is T1, and this is our pulse length. So when counter is smaller than a pulse length, That is, when we are here, the value will be high. If the counter exceeds the pulse length, then the LED value will be 0. So this is our LED. And by using this simple if statement, we can produce a pulse width modulation signal. In this code, I'm producing a pulse width modulation signal with a period of 4 milliseconds and with a pulse width of 2 milliseconds. Now you can stop me over here and ask me the following question. How did I calculate these values? That is, how can I transfer period length, pulse length, and my counter into seconds? Well, it's quite straightforward. You just have to keep in mind what is your period of the clock of the system. In my case, that's 10 nanoseconds, and mathematically that's 10 times 10 to the minus 9. Then you just need to multiply the clock period with the period length of your pulse width modulation signal, and you can get the period of the pulse width modulation signal. Consequently, since I have over here in my code, let's see that, 400,000 for my period length, basically I have 4 times 10 to the 5 multiplying 10 to the minus 9, and that produces 4 times 10 to the minus 3. That's 4 milliseconds. Similarly, we can compute the pulse width that is equal to 2 milliseconds. Obviously, you can change these parameters, period length and pulse length, to achieve any desired shape of the pulse width modulation signal. And furthermore, you can modify the code by basically providing over here period length and pulse length as inputs or as parameters. However, to keep this video short as possible, I will not do that. As a side comment, keep in mind that these values of period length and pulse length are different from the values that you saw on the oscilloscope at the beginning of this video. Namely, at the beginning of this video, I used much higher period length and pulse length since I wanted to make LED to blink. That is, you need to select period length to be in the order of, let's say, 1 second and pulse length of 0.5 seconds, such that you can see LED blinking. However, if you put these values as they are, and if you synthesize your code and create a bitstream, you will not see the LED blinking. So keep in mind that. Okay, so that was our source code. The next step is to define the constraint file. So let us explain what is a constraint file. Basically, you need to tell to Vivado and to Verilog where is your clock and where is your LED. By just keeping the code as it is, you can run this code in a simulation. However, you cannot run it on hardware. So the first step is to find the pin on your board that corresponds to the system's clock. So how to find that pin? That's a very good question. To find this pin, you need to look into schematics and manual of your board. So I found the schematics and the manual of my board, and they're given over here. So let's find the clock and let's find the other pin, the LED pin. Okay, so what I will do over here, I will just search for clock. And you will probably need to go down. I think this is basically a section number 5. We need to find the section number 5. And over here, you basically see the explanation. And it's clearly saying the following. The Nexys A7 board includes a single 100 MHz crystal oscillator connected to the pin E3. So the pin E3 is the pin that corresponds to the system's clock. So let us constrain this pin. How to do that? Over here, I've wrote a code that I will simply copy and paste. And of course, this code is given on my web page and in the tutorial. So let us create a constraint file. Over here, I will click on Add Sources, and I will click on Add or Create Constraints. Here, I will click on Create File. I will call it const. Click on OK. Click on Finish. And your constraint file will appear here. It has the extension XDC. So let's create the constraint file, and I will simply copy and paste this part over here. Basically, I'm setting the property package pin E3. So here's where I do, and over here I constrained it to the clock variable. So this code line is basically saying the input to our module, that is clock, is actually pin E3. Okay, here you need to define, or better to say declare, the period of the clock. By reading this website, you can see that it's 100 megahertz, and 100 megahertz corresponds to 10 nanoseconds, and consequently over here I have 10. And this code line is pretty much standard. You're using the standard LVC MOS33 standard, and you just copy and paste this part. I will not explain this part in more details. Okay, so let's go back and let's constrain the output. That is, we need to constrain the LED signal. Let's go back to my website, or you can also read the schematics description over here. However, I extracted all data over here. Now, this pin over here, the pin given over here, is actually H4. How can you find that pin? Well, again, open the schematics file, and you need to scroll down and look for PMODs. So let's find the schematics. Okay, so here's the pin description. Is pretty much standard for every PMOD, and notice here that I have 1, 2, 3, 4, 5 PMODs. I'm looking into this PMOD, and this PMOD has the notation JD. Consequently, over here I can see my JD, and I can see that JD1, that is the pin 1, or the pin over here, is H4. So let's constrain that pin. So here's how we constrain that pin. We are basically saying, set property package pin H4. So H4 is constrained to the port LED. And that's it. Of course, you need to add this code line, and after adding this code line, you are basically done. You completely constrained inputs and outputs of your module to the physical pins and ports on your board. Make sure that you save these files, and let's generate a Bitstream. So I will click over here, and I will click on yes. I will click on OK. And this process will maybe take 1 or 2 minutes, or maybe 5 minutes, depending how fast is your computer. So after several minutes, the process is completed, and over here I will click on cancel. So let us open the hardware manager, and let us upload the code. To upload the code, you first need to connect your board to the USB port, and over here you need to click on open target. Then you click on auto connect. This will take some time, connecting to the server, establishing basically serial communication, and everything should be fine. So let us upload the code. Basically, you can expand this section over here, and you do the right click and you click on program device, and you simply click on program, and then you will get this window programming the device. Now your device is programmed, and if you attached your breadboard to proper ports, you will see basically that the LED is on. Now, to make the LED blink, you need to simply change these values over here. For example, over here you need to select a value that will produce seconds, for example. That is, you need to multiply this by 1000. So you will add 3 zeros over here, and you will add 3 zeros over here. Then again, you need to repeat the whole process. You need to generate the Bitstream, and then again, you need to basically open the hardware manager and program the device. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.